Hello and welcome to Wednesday, April 29th lesson in Chemistry 12-2. First of all, let me say again how extremely proud I am of you and the work you're doing so far. The fact that you're watching this video makes me very, very happy. Please watch it to the end so you don't miss anything. This is the second half of section 19.2 from your textbook. So although on Monday I asked you to read the entire section, we actually only covered the first half in Monday's lesson. So here is the second half of lesson 19.2, talking not only about KW, but soon you will find out talking also about something called pH and pOH. So let's get started. First of all, in reviewing for the end of our unit assignment, that's right, I said it, we are almost one unit done. In preparation for that, I was going through the curriculum, making sure I covered everything, check, 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 check. And there was something that I didn't feel I covered very well at all. So I'm just going to start by going back to looking at what are called reaction mechanisms. So here's one example, here's another example, and then this third example I'm going to ask you to do. So for this first example, sometimes, as I said earlier in this unit, reactions don't take place in one step, but rather they're a series of steps. So this reaction has two steps to its mechanism. First, we start with hydrogen and iodine chloride, but we end up with iodine and hydrochloric acid. It's a two-step process. So the first thing I would ask you to do is take note of what appears on both sides. In essence, what can I cancel out? So I'm going to choose something, let me see, maybe yellow might show up. And I'm going to say, okay, I have an HI here and an HI here. So it's going to cancel out. And let me see what else. I think that's it. I think that's all that I'm going to be able to cancel out. So because it appears on both sides, but is not in the overall reaction, it's canceling itself out, it's called an intermediate. So that is something that's created, but then used up again in the next step. So it's created in step one, but then used up in step two. So the intermediate in this case is HI. Okay, next thing I want you to do is look to see if there's anything that starts out over here in the reactants and appears again in the final products. So is there anything up here that appears again in the final product? And I would say no. So that means that there was no catalyst. Okay, there was nothing added to this reaction to make it go faster and then found at the end again. Okay, now let's combine these and see if we can't get the overall reaction. So the overall reaction is what you have once you combine the steps. So you'll see I have an H2 on the left, no more on the left, and none on the right. So this is kind of like what we used to do for Hess's law. So I've used up the H2. I have an ICl on the left, and I have another ICl on the left. So that means I have two ICLs. Oh, it's going to be a fun morning. Here we go. 2ICL. Okay, now that has covered everything on the left side. So now I'm going to look at the right side of the reaction, the product side, and you'll see I have an I2. And you'll also see I have two HCl's. So hopefully when I take a peek at that, that is balanced, two H's, two H's, two I's, and two Cl's. So that's my overall reaction. The overall reaction can only be as fast as the slowest reaction. So therefore this overall reaction is going to be slow. Because of my two choices, slow is slower than fast. Okay, so again, that's a reaction mechanism. In this case, it's two steps to get from the initial reactant to the product. Let's take a peek at this one. Nope, let's go back to this one. There we go. Okay, so again, let's see if there's anything that's appearing on one side and canceling out on the other. see if I can't find a funky color again. Let's go with this pink. So I have an N2O here that was formed up here. So it was formed in step 1, removed in step 2. Okay, so that's what we call an intermediate. So intermediate. And again, that was our N2O. And then let me see if I have anything that's up here and down here. No, so I don't think this one has a catalyst because there's nothing in step 1 reactants that appears again down here. Okay, so there's no catalyst in this one. And can we cancel anything out? We've done that already. So I think it's just time to combine them. So the overall reaction, let's look at the left side. We're going to see 2 molecules of H2 and 2 molecules of nitrogen monoxide. And on the right, for our products, we're going to see a molecule of N2, and we're going to see, oops, there we go, 2 molecules of H2O. Come on. Oh, this is a fun game. There. All right, and of course the speed of the overall reaction is going to be slow because you can only be as fast as your slowest step. All right, so now we are ready for you to practice. So take a look at this one, please. I need to know if there's a catalyst present. Who is it? I need to know the intermediates. Could be more than one. And I want the rate determining step. Then when that's all done, I want you to give me the overall reaction equation and tell me if the equation or the reaction rather is fast, very fast, or slow. Pause the video, make your best guess, and then start the video up again, please. So for the first thing, you should have looked at for a catalyst. A catalyst, again, is something that you find in step 1 in the reactants that you find again in the product. So it's unharmed. It's been used up, but then it appears again. And in this case, you should have noticed that H+. Okay, H+ appears as a reactant. It appears again as a product, and it was used up in between and then appeared back. Okay, intermediate, something that you see produced and then used up. Produced and then used up. In this case, there are 2. It's kind of funky how they changed how they wrote this out, but that is indeed the same chemical species. They've just put the 2 O's together and called it O2. So yes, there are 2 intermediates in this particular case. The rate determining step would be the slowest of the 3, so that's step 2. And then once you combine those, cancel out the H pluses, cancel out the intermediates, and so on, your overall reaction should be like so. Okay, so again, that was something the first week that I had mentioned reaction mechanism. I talked about each of those things, but hadn't given you a specific example to try. So I wanted to make sure I did that. Okay, a review of yes, oh, pause. That's an old one, of course, so many of you probably knew right off the bat, tuna. Not to be confused with tuna from The Office, of course, poor little Jim. Okay, so from last lesson, this is what you should remember. We learned something called an equilibrium constant for water. Its value is 1 times 10 to the negative 14 moles per liter squared, and that's only if the temperature is 25 degrees Celsius. That's very important, and we'll see that before the class is out today, why that is so important. Okay, so again, I'm hoping you're keeping a green sheet so you have it nice and ready and close to you when you get to post-secondary, and on that green sheet you should have those 2 things added. Kw, the equilibrium constant for water, is the result of the product of the concentration of the hydronium ion, or the hydrogen ion, or the H+, or the proton. Those 3 terms, remember, refer to H3O+. hydronium ion, hydrogen ion, and proton. So Kw is the result of the product of the hydrogen concentration, hydrogen ion concentration, and hydroxide ion concentration. This was the question I left you with on April 27th. And while you watch that very quick movie clip or video clip from AP Chem, I said one of the hints was that you would have a question like this for homework. They were talking about hydrochloric acid. And at the time, they showed you the equation for the ionization of hydrochloric acid, the breaking apart of hydrochloric acid. So the first thing I would suggest you do with all of these types of questions is write out the ionization, what's actually happening. Hydrochloric acid is a very strong acid. Now, there is something called an acid and base table, which I had hoped to be able to give you. There we go, an acid and base table. However, since we're not in the school, it's a little bit challenging to give it to you. You did have a heat table for your thermochemistry unit, and I think I tried to photocopy the acid and base on the back of that. So if you have your heat table, look on the back of it, and you should see an acid-base table. If not, I will be posting it to files so that you'll have access to it, but you're going to need this acid-base table. When you look on that acid-base table, you will find 6 acids are very, very strong. This hydrochloric acid is a very strong acid. So again, there are 6 acids that are very, very strong. We will talk about them in detail next unit. But for now, just trust me when I say hydrochloric acid is very strong. So that means it will break apart like so. You can see a single-headed arrow because 99% of it breaks up, okay? And that's because it's a strong acid. And again, whoops, let me just steal that, okay? And I'm going to put at the top, it's 1 of 6 strong acids. Okay, so that's what hydrochloric is. And again, we'll review that and we'll talk about that next unit. But in the meantime, just trust me when I say it's one of the 6 strong acids. So we know it breaks apart 99%. Okay? Now we know the concentration of the hydrochloric acid is 0.15 moles in every liter. So I'm going to put that right over the top here. 0.15 moles per every liter of HCl. Now, if you break that up quantitatively and you have 0.15 moles per liter of HCl, it makes sense then you would also have 0.15 moles in every liter of H+. Because you just have an H, let me see where this is going, there we go, an H, there we go, HCl, and that breaks down into an H+, there we go, and a Cl-. So if you have 0.15 of these in every liter of water, you should therefore have, if you break them apart, 0.15 of these in every liter and 0.15 of these in every liter. Okay, so that's where I'm getting this next line. Whatever the concentration is for the acid, that's also the concentration for the H+, 0.15. Now that we know the H+, and we have a Kw expression, we can simply plug that into our Kw expression. All I did here was rearrange it. So let me go back to the slide. This equation right here, just going to steal that. And all I'm doing here is rearranging this equation to get that. So I can solve for my hydroxide. Okay, that H+ and the hydroxide are not going to be equal because we're talking about an acid here. It's not a neutral substance, it's an acid. So if we're talking about an acid, make your guess right now. Do you think the H+ is going to be higher in concentration or the OH- if we're talking about an acid? Perfect. That's right. You should have said the H+ is going to be higher because we're talking about an acid. So we take our 0.15, we use our Kw, we plug it in, and we find that the hydroxide concentration is 6.7 times 10 to the negative 14, which is indeed much smaller than 0.15 moles per liter. So that makes sense that this is an acidic solution since the H plus is much higher than the OH minus. So again, because it was a strong acid, we can infer that the concentration of the HCl is the same as the hydrogen ion. Once we have that hydrogen ion, we can plug it into our Kw and get our OH minus. Okay? Moving on to another example, we're now talking about sodium hydroxide. So we're looking at the hydrogen ion and hydroxide ion concentration in sodium hydroxide. A couple of different things here. First of all, your mean and nasty teacher didn't give you a concentration to start with. She gave you a mass and a volume. So you should have noticed right off the bat, you're going to have to change that mass into beautiful, yes. The sign to the chemist's best friend, the mole. So we take that, oops, there we go, 2.6 grams divided by 40 grams, which is of course the molar mass of sodium hydroxide, and we get that many moles. Then we're going to divide that by 500 to get its concentration. And remember that milliliters, which should be in uppercase L, I might add. I have a bad habit of doing that. That 500 milliliters is the same thing as 0.5 liters. Remember, there's quite a few of us that have a problem transferring or converting from milliliters to liters. You move it 3 places to the left, the decimal that is. Okay, so we have our concentration of 0.13 moles per liter. So we're now pretty much at the same place we were in this question initially. Here initially we had 0.15 of hydrochloric acid. Here we have 0.13, but it is of a base, sodium hydroxide. Sodium hydroxide. Now, I will tell you that anything that contains OH, there we go, is a strong base because it has OH attached to it. And again, we'll talk about that more when we get to the next unit. But for now, trust me, it has OH. It's a strong base, which means single-headed arrow, it breaks apart quantitatively, forming Na plus and OH minus. Now, if we know that the concentration of the NaOH is 0.13 moles in every liter, then we also know there's 0.13 moles in every liter of hydroxide. There's no H plus present per se, at least not a significant amount, so we're not showing it. So this concentration is the same for the hydroxide. Alrighty? Then we can use our Kw, plug in our values, and find out that the H plus is 8 times 10 to the negative 14. It's actually 7.7, but because of the significant figures, I only brought it to 1. At 500, we chemists call 1 significant figure, so that's why I have 1 in my final answer. A couple of things I want you to note. Again, it's a strong base, so that's how we know it breaks apart into these two pieces. This sodium is just what we call a spectator. It's not contributing to the overall behavior of the substance. It's just kind of hanging out. We care about the OH. Okay. The second thing I wanted you to notice is that it's what we call a one-to-one relationship. This is one-to-one. There's 1 sodium for every hydroxide. Similarly, there was 1 H for every Cl. I'm going to change that up in the next equation. Okay, and 1 more. So the third one, as I said, we're going to look in this case at what's called barium hydroxide. And those of you that were looking very carefully, you saw that I had written out the chemical formula. This one's a little bit special because barium has a charge of +2. It's from group 2 on the periodic table. Hydroxide only having a charge of -1. So when you write it out, it's actually going to have 2 hydroxides for every 1 barium. Very, very important. Now I'm going to try and squeeze something in here. I'm just trying to group that. Hopefully. A little bit slow. Very early in the morning. Doesn't want to. Okay, let me try this again. I just want to, oh good. Okay, all our, you know what? I'm just going to write underneath instead. So underneath, I am going to write, let me see, choose purple. Oh, good. This is funky now. All right. So underneath, I'm going to write that 0 point. Okay, come on, tape. Get it together. This is really funky. There we go. 0.25 moles per liter. Now you can probably already see the surprise I'm trying to hide, but anyway. Come on, little critter. This is a lot of fun, watching the teacher try and use her smart stuff here. Okay, anyway, so there's our concentration of barium hydroxide, okay, which they gave us in the question, 0.25. And what I'm trying so desperately to show you is that I cannot put that same value over here, because in this case, it's actually 2 times that amount. So it's 2 times 0.25, because there are 2 hydroxides for every 1 barium hydroxide. Does that make sense? Yeah. So barium hydroxide is made up of 1 barium, 2 hydroxides, 1 barium, 2 hydroxides, 1 barium, 2 hydroxides, 1 barium, 2 hydroxides. So if the concentration for this whole has a 1 in front of it, 0.25 for every 1, then it's going to be 0.5 for 2 of them. Very, very important. One of the most important things this lesson is that you notice that stoichiometry is important here. Okay? Now that we know that's doubled, our concentration of hydroxide is 0.5. It's simply a matter of plugging it into our Kw expression, which I have messed up here. Boop, boop, boop. There we go. And we get our H+, which is this. Alrighty. Easy, aside from the painful use of the smart notebook software. Okay, moving along. Now, for that one, I'm going to keep you in suspense. So screenshot that, try and find out your answer, and then go back to your notes later today and see if you deduced who the nasty culprits were. Okay. Communicating concentrations using pH and pOH. This should be old news for you, those of you that have taken upper level math courses using logarithm, etc., etc. I know Mrs. Baker does this in her class, and I know sometimes she uses pH as an example. There was a scientist years and years ago, his name was Søren Sørensen. He was a Dutch chemist, and he said that these concentrations that we're talking about, of, in this case, let's say the hydroxide or the H+. I mean, look at this hydronium ion. Look at that concentration. I mean, that's itty bitty. That is 2 with the decimal move 14 places to the left. I mean, that's a really tiny number. Similarly, this one, 7.7, the decimal move 14 to the left. He said, you know what, that's a little bit ridiculous dealing with those numbers. So let's put them on the logarithmic scale, and let's just say they're going to go from 0 to 14. That's what our pH scale is. It's a lot easier to talk about the concentration of hydronium or hydroxide if we're dealing with numbers 1 to 14 or 0 to 14 rather, as opposed to these itty bitty teeny tiny numbers 10 to the negative 14, etc. So for this, you need a scientific calculator. You must have one. So if you don't have it with you, pause and run and go get it, please. Okay, you need your scientific calculator. This is not going to make nearly as much sense if you're not able to plug those numbers into your own calculator as I do so. All right. So run and get your calculator, come back and press start again. Okay. So here we are, pH scale. Again, it goes from 0 to 14. These are your 2 equations. I'll talk about those in a second later. The pH and the pOH must equal 14 unless pure water. Okay, and we'll talk about that later in this class. So unless it's pure water, the pH and the pOH have to equal 14. Okay, all right. I'm going to jump right into an example. Communicate a hydrogen ion concentration if you know this. Okay, this is the hydrogen ion concentration. Communicate that as a pH value. So again, your formula, your equation rather, pH is equal to the negative logarithm of the concentration of H+. So some calculators ask you to start with negative and then log. Some calculators ask you to start with a concentration and work backwards. So looking at your calculator, try it this way first. Press negative, log, and then the concentration of H+, and you should get this. Okay, if that does not work for you, then do it in the reverse order. My calculator always seemed to like things backwards. So on my calculator, I would put in the concentration, then I would press log, and then I would press negative. So depending on your calculator. Only other thing I want to point out here is significant figures are kind of wonky. If there's 2 in the concentration, it means there's 2 decimal places in your pH. Okay? The other thing that I mentioned on the previous slide is that the pOH and the pH have to total 14 unless it's pure water. So that means in this case, the pOH is going to be 14, subtract 10.33, and without a calculator, let me see, is that 0.67? That makes it 11, so 3.67. No comments, please, about how long that took me. It's very early in the morning. I'm not telling you the time, but all right. So that's all you have to do with that. And then the other example here is to go backwards. So again, to go backwards, you log, okay? So you're just going to put 10 raises to the negative 10.33. And again, that's going to be different on each calculator. So just practice with yours and see what buttons you push. I'm not going to fib grade 12. If we were in the classroom, we spend a lot of time with me walking around the classroom, making sure everybody knows how to use their calculators. Very, very important. You know what numbers to punch in. All right. So please, please, please try these and write it down on your green piece of paper so you remember how to do it on your calculator. Again, 2 decimal places in the pH. So my final concentration is going to have 2 sig figs. Okay. Now, I can also take that H+ concentration and use my KW to find my OH concentration and work back and forth. And you'll have practice with that in tonight's homework. So take a screenshot of that. Very important information. That's what we've covered so far. And again, I'm adding not pure water at the bottom because that's where I'm going to close this lesson, is talking about pure water. Okay, these are for solutions that are not water. Because as you learned yesterday in the video, for water, pure water, the concentration of H+ has to equal the concentration of OH-. Okay, Mr. Fairbot in the video showed you little particles, and he showed you there were 4 hydronium ions, 4 hydroxide, so that's how we knew it was a neutral solution. Okay, lastly, you're being very, very patient, very kind, and I'm hoping you're watching this whole entire video. This is our second to last slide. Let's revisit the autoionization, which is also called self-ionization of water. So in the video yesterday, you saw water molecules, one giving up an H, the other accepting it, so we ended up with hydronium and hydroxide. If there's an equivalent number of hydronium and hydroxide ions, we have pure water. So just using my screen cover here, and reviewing a few things. Kw equals hydronium ion multiplied by the concentration of hydroxide ion. Easy peasy. Okay, perfect. In pure water, those concentrations are equal to one another. Okay? So if we know the Kw is this, we can take the square root to find the concentration of each the H3O+ and the OH-, which again, in a neutral solution, is 10 to the -7. Moles per liter. All right. Trying to put a little m in there. But anyway, that's fine. Okay. However, remember, that is only at 25 degrees Celsius. All right. Only at 25 degrees Celsius. Okay. I should learn how to, I'm sure it's possible, to make that flash so you never forget. There it is flashing. Okay, so that's at 25 degrees Celsius. Now, Closing thoughts. Here we go. Think about this. If I told you this was an endothermic reaction, which indeed it is, endothermic, where does the energy belong if it's an endothermic reaction? Endo. Okay, I'm hoping you're telling me that it means that it's on the left side of the equation. So let's think about this. If I warm this reaction, if I heat this water up, what happens to the concentration of the ions H3O plus and OH minus? If I heat it up, I'm adding energy. Which way is the equilibrium going to shift? You should tell me it's going to shift to the right. And if it shifts to the right, what happens to those concentrations? They go up. Okay? Now, what does this mean about the pH and the pOH? Remember, it's the negative log. Okay? So, the concentrations are going up, then the pH and the pOH are going down. So, if we actually had hydronium ion concentration of 10 to the negative 6, the pH is now 6, but it's still considered to be neutral because the H3O plus equal to the OH minus, oops, that should be a minus, I'll have to fix that, means it's neutral. Okay, so even though the pH might be 6, it's still neutral. If the pH of water at 10 degrees is 7.25, what is the pOH of water at 10 degrees Celsius? pH, pOH have to be equal if it's pure water. So if the pH is 7.25, okay, lower temperature, the pH goes up, then the pOH is going to be the same. Okay, a lot of information. Remember that tomorrow we have extra help with chemistry. And tomorrow you should also be working on worksheet number 3. So while you're working on worksheet number 3, if you need any help, I will be online from 9 a.m. till 11 a.m. We have been asked to keep to our normal class time for extra help. So I'm putting it back to 9 a.m. and 11 a.m. Period 1, 9 a.m. kind of hits you. Period 2, 10 a.m. kind of hits you. So I thought if I did the 2-hour range, I would hit both of my classes. Okay. So in closing, take a screenshot of that for your green sheet. Okay, and remember that's to do with water, pure water. And your homework is to work on worksheet number 3. And again, please, please, please check in with me tomorrow morning between 9 and 11 on Teams, and I will give help wherever needed, or just to say hello. Your credit assignment for this week will be arriving with Friday's lesson. You'll have a few more days to work on it. Thank you, grade 12. Bye.